Because remember that the definite integral from a to b of f of x dx gives the net area, we have to take some other steps if we want to find the total area, just to be sure that we've got it when the function intersects the x-axis. For example, check out this function here, 3x squared minus 3 from negative 2 to 2. So we're going to start here at negative 2 and end here at 2. We talked about how this area will be positive above the x-axis, but then this area down here below the curve in the x-axis will be negative. So if we did the definite integral of this function, we'd find the net area, not the total area. When looking for the total area, and just read the question, if it says total, consider the fact that the function might have area below and above the x-axis. To account for that, we first want to find the zeros of the function. That's where the function equals 0, and then use those zeros to subdivide the interval, then integrate over these subintervals and add the absolute value of these areas to find the total area. So here's an example. Like I said, we have two zeros of the function. To find out where those zeros are, we are interested in when 3x squared minus 3 equals 0. And you can see that this happens when x is equal to plus or minus 1. So those are the zeros of the function. So to find the total area from negative 2 to 2, we will not do this, the definite integral from negative 2 to 2 of 3x squared minus 3 with respect to x. That will give the net area, like I said, positive minus negative area. We will instead divide this integral from negative 2 to negative 1, 3x squared minus 3 with respect to x. And then the next subinterval is from negative 1 to 1. The function is 3x squared minus 3 with respect to x. And then from 1 to 2. And then the third interval from 1 to 2 of 3x squared minus 3 with respect to x. So we found the zeros of the function. Now we divide the interval up and integrate over each subinterval. So we had interval a, integral b, integral c. A, b, c. To find the antiderivative of this, remember, we'll go up one power, so x squared becomes x cubed. There's already a 3 there, but we'll divide by 3 also because we've gone up a power. And the antiderivative of 3 is 3x. Then we're interested in evaluating this from negative 2 to negative 1, which means plug in negative 1. So I'm going to get rid of this 3 over 3 and say I have negative 1 cubed minus 3 times negative 1 minus negative 2 cubed minus 3 times negative 2. So negative 1 cubed is negative 1, negative 3 times negative 1 is plus 3, minus negative 2 cubed negative 8, 3 times negative 2 with a minus is positive 6. So this negative 1 plus 3 is 2, minus negative 2, 2 plus 2 is 4. You can follow the same process. It's the same antiderivative for the function here. We just change the limits, so we still have x cubed minus 3x evaluated from negative 1 to 1, and x cubed minus 3x evaluated from 1 to 2. Probably from symmetry from the picture, you're confident saying that integral c is also equal to 4, and integral b equals negative 4. Believe it or not. The negative is easy to believe. It is underneath the x-axis. So if we want to find the total area, we can sum the absolute values of these. Integral a adds 4, integral b adds 4, integral c adds 4. Because each of those pieces are worth 4, the total area is 12. We can also use this concept to find the area of a shaded region when the region is defined by more than one function. For this example, we have secant squared t for negative values and 1 minus t squared for positive values. Now there's a lot going on in this. The first thing you might notice is that the shaded region is above the curve, not below the curve. And then the second thing is that we have these two different functions. So to find the shaded area when it's above the curves means that maybe we should consider the whole rectangle and subtract the area below the curve. We can find this area underneath the curves using the definite integral. And if we have the area of the rectangle, we can subtract the area under the curve to get the area above the curve. The area of the rectangle is just the length times the width. The length of the rectangle is 1 plus pi over 4. 1 on this side, and then another pi over 4 on that side. So 1 plus pi over 4 gives us the length, or the width, and then we need the height of the rectangle, which is 2. So the area of the rectangle is 2 plus pi over 2. Then we have to subtract the area below the curve. So let's talk about this area below the curve. We can find it with definite integrals. This first guy is the definite integral from negative pi over 4 to 0, right? That's the x values we consider. And the function that defines the height of the rectangles would be secant squared t with respect to t. So that takes care of like this left-hand side over here. Then on the right-hand side, that's the definite integral from 0 to 1. Those are the x values covered there of the curve 1 minus t squared with respect to t. So now we need to find antiderivatives and evaluate. They both have their different limits. The antiderivative of secant squared, as you remember, is tangent of t. We'll evaluate that from negative pi over 4 to 0. And we need the antiderivative of 1, which is t. Antiderivative of t squared is 1/3 t cubed, evaluated from 0 to 1. Sometimes you'll see people put a little bracket there that says we're going to evaluate all of that from 0 to 1. So now we'll do it the tangent of 0 minus the tangent of negative pi over 4 plus this first thing evaluated at 1 minus 1/3 times 1 cubed minus 0 minus 1/3 times 0 cubed. Now we evaluate that. The tangent of 0, that's sine over cosine of 0, is 0. The tangent of negative pi over 4, remember negative pi over 4 is here, so the sine of negative pi over 4 is negative square root 2 over 2, and the cosine of negative pi over 4 is positive square root 2 over 2. When we make sine over cosine, we get negative 1 just for the tangent, plus 1 minus 1/3 minus 0. So here we have 0 minus negative 1 is plus 1 minus 1/3 for our area, which is 1 minus 1/3 is 2/3, so 1 2/3, or we could call that 5/3. Okay, so we got 5/3 for the area below the curve and 2 plus pi over 2 for the area of the rectangle. Now we just need to combine them. So the area of the shaded region, 2 plus pi over 2 minus 5/3 is 2 plus, nope. So 2 minus 5/3 plus pi over 2 is 6/3 minus 5/3 plus pi over 2. 6 minus 5 is 1. So that's 1/3 plus pi over 2. Not such a pretty answer, but an answer nonetheless. You could put this in your calculator and get an approximate value for the area here. We should not be surprised that it's defined in terms of pi since trig is involved. And now we found the area of the shaded region.